Welcome back to my lectures, and let me recall, we are discussing BurnsideRing of a Lie group, and we also illustrate the usage of computer software, namely the usage of GAP equipped with the package EquiDeg. So let me begin, and let me start with the topic. Let's say I call it notations. And examples. So let me underline. This is our topic. So first, I would like to introduce something which we'll call the twisted notation. Twisted. And more about the ways how this notation is applied, I would recommend to look into our previous book, the book that I listed in the previous lectures, namely our book, The Applied Equivariant Degree. I think on the list of the references it was the number 1. And let me begin. So let's say given a group, I call this group gamma. You can think about it. For example, take the group which is like a pDihedralGroup of n-gon, or as a symmetric group that permutes n elements, and we are actually interested in the group which is we consider the group, the product group, and I call this group G. My group is just exactly gamma, so I should write here, equals gamma times Z2. That's the simplest case when this notation could be used. So the question is, how can we describe up to the conjugacy classes subgroups of the product gamma times Z2, namely this is our group of interest of these products. Okay, one can immediately notice that there are two different types, or there are two types of such subgroups. So the first type is exactly the groups of the type of the product. So first type, let's say the product. The products, and we'll put it like this, a subgroup H times Z2. So what is H? H is the subgroup of gamma. So that means those are the products of subgroup of gamma times the whole group Z2. So let me introduce the notation. As I said, this will be notation. So for example, if we have the name of such a group H, we call this for example H, then I will introduce the notation. I will just here put P. So HP means this is a product group, and that means exactly H times Z2, it will abbreviate this longer symbol, which is kind of this notation is kind of useful. Notice that writing these products may be kind of annoying. So this is, in this case, the case. So this is clearly a case of a product group which can be written just simply HP. H product Z2, HP. The second type of the subgroups, those are the groups we will call twisted. They are graphs of homomorphisms. So let me write it down. Twisted subgroups. And those twisted subgroups are related to the following. So for example, we have the group H, which is a subgroup of gamma. We also have a homomorphism from H to Z2. This is homomorphism. Then we can define the group which we call twisted subgroup. So this is H5, and this will be the set of all H. Here I put here Z because like a Z complex number, but basically this is plus minus 1, belonging to gamma times Z2, satisfying the property that this phi of H is equal to Z. So you can clearly see that this group is the graph of the homomorphism graph, homomorphism phi. We call it twisted. Twisted. So this is the twisted, and with that one we call the twisted notation. This is twisted notation. That's a twisted notation. So in particular, if you think about the subgroups, so first of all you can think about subgroups of H. These are subgroups of gamma, and take the homomorphism, which is the trivial homomorphism. So that means it maps the whole subgroup H into the neutral element of Z2, which means 1. So that's contained in Z2. So this is trivial homomorphism. Yes, so in such a case, what is this H? Phi is clearly, in this case, H times element 1, neutral element in Z1. And for the convenience, we can see what? Basically, that's the H, so we'll call it H. So in such a case, we can see that the subgroups of gamma are also twisted, and they be considered just as the twisted subgroups corresponding to the trivial homomorphism. So, of course, if a homomorphism is non-trivial, so the second case is that you have here H, and then you have here gamma, and phi from H to Z2 is not trivial, so that means it must be epimorphism. And in this case, we have, let's say, all kinds of the different subgroups which are. Notice that in each case, if you have here H phi, so notice that this is homomorphic to H. So if we are using this notation, basically this notation gives you an idea what is the structure of the twisted subgroup. In this notation, it just simply explains to you that, okay, this is twisted subgroup, but basically as a group, it's exactly the same as the symbol standing here means H. H is how this group so what is the structure of this group? Exactly this is the same as the structure of H. They are isomorphic. So let me give you an example. So first of all, we will be dealing with this notation. So we need to somehow explain that this notation we would like to implement in certain way, let's say, computational scheme. So it will be easier for us when we do the computations to recognize the symmetries, related symmetries, those subgroups or those conjugacy classes that we are considering will be related to certain symmetries. So having a notation in which it can be, let's say, deducted more easily what kind of a symmetry it is, it would be kind of a, let's say, advantage. So our first example, let's consider example, and let's consider the all possible subgroups. So I consider here the group G, and this group will be D5, and this will be times Z2. So we already know, and we want to classify all the conjugacy classes of subgroups. So we will be, let's write it down, classify conjugacy classes of subgroups in G using twisted notation, using twisted notation. Let's say, okay, so, and abbreviation. So we'll also use the abbreviation. And abbreviation, put it like this. And maybe I write this clearly. Abbreviation. That, what do I mean by abbreviation? That means I would like to abbreviate these symbols. Those are like symbols using superscripts, subscripts. Maybe this is difficult when you would like to put it into your, let's say, script for the program or write something. So better to have kind of a notation that could be, let's say, implemented into the program. So that will be just illustrated in a moment. So let's start it using twisted notation. So of course, the subgroups, we have the following. So of course, the first one is the A. So we have the products. So we have here Z1, P, then we have here Z5, P, and then we have here, okay, D1, P, and of course we have here D5, P. Those are the products. So this is H times Z2 is denoted HP. Okay, so then we have here the B. So first part is just simply the subgroups of gamma, in our case D5, so this will be Z1, and this will be Z5, and this will be D1, and this will be D5. And then we have here other, so that means we need homomorphism. So clearly you don't have homomorphism, epimorphism from Z1 to Z2 or Z5 to Z2, but there are such homomorphisms for D1 and D5, and we will denote this epimorphism from D1 to, from any Dn, so it will be used kind of all over, everywhere where we apply it, so it will be for any dihedral group, so you have here like this, from any Dn, maybe I must write it more clearly, 2 dots, Dn goes to Z2, so this is a homomorphism, clearly kernel of Z is equal Zn. So in such a case, I have here the following notation, so it comes that we have here D1Z, those are the twisted subgroups, and D5Z, and that's it. So those are all possible representatives of these twisted subgroups, of the twisted subgroups. So let's look at another example, an example that may be, let's say, more sophisticated, let's say, kind of more interesting, especially when you are thinking about the real symmetries, that examples help you to maybe visualize that let's say connections between the symmetries and algebra. So this is another example. In our case, I consider gamma is equal to S4, and that means this is the group of permutations of 4 elements, and this group actually we will identify as the symmetry group of octahedron, namely that means this is also called the octahedral group. So this is octahedral group. Octahedral group. So let me illustrate this group by using the cube. Cube and octahedral are dual, so I can use the cube for these purposes. So just simply see. My cube looks like this. And then I take one. This is my cube. I don't really need that one. Let me remove this one. Okay, try to remove it. Okay, I'm removing. And here it has to be dotted. So let me, okay. And so we have this octahedron. So how the group S4 acts on this cube? What does it permute? In this case, when you look at this one, you don't see what does it permute, but actually there is something to permute. Notice that this group permutes the diagonals. So we have 4 diagonals in this cube, and let me kind of a ugly picture, not really. Yeah, kind of. Okay, I need to remove it, the picture. It never works. If the picture is bad, it will never work. Okay, so let's start again. So I need this one, little shorter. This one is longer, and then this one, and you see all 4 diagonals intersect in one single point, and that point, okay, didn't happen to be in the right location. So if I have here this diagonal, take that diagonal, and then I have here next diagonal. It's all intersection in one location. So those are 3, and now I have also the 4th one, which goes like this, kind of invisible. So in any case, you can notice there's a 1 diagonal, there's a 2, starting from this vertex, and there is a from 3, that's this one, and the last one will be 4. So if you look at this picture, so the transformation that will be, let's say, the symmetry transformation that will be transforming this cube to itself will be a transformation that applied to these diagonals will change their position in this picture, will permute these diagonals, And actually it is kind of interesting that if you look at this particular picture, you can immediately recognize that the certain subgroups of S4 corresponds to the specific geometric symmetries. Namely, if you look at this cube and you just look at one of the faces of the cube, so this is your cube, and I look just simply like from the top, for example, I look at the cube from the top, so I can see square. And I know that if I have a square, I also have symmetries. Square has symmetries. This is D4. So this is dihedral group of a foregon, that means of 4 vertices of a polygon. So that's one. And then if you look at the cube just simply from the direction of any of diagonals, you will see something that looks like a hexagon. The hexagon, first you see that this is just simply a hexagon. That's like, it is a shadow. And then of course you can notice that there is a additional elements in this picture, and that's your cube. But you see a hexagon. So from that point of view, since here you can clearly see this is 1, 2, and 3, those edges are in the picture, cannot be, if you apply any transform, they have to be preserved. So basically you can see that this is the same, any symmetry that preserves this particular, let's say, picture would be symmetry of a triangle. Symmetry of a triangle. So that means that here we are dealing with the dihedral group D3. And then, of course, if you look at the diagonals, in this case, diagonals of the sides, so maybe I make another picture. I don't want to mess up too much. So if I take another picture and change it to red, so I can take the one diagonal, another diagonal, another diagonal, and then you have another diagonal, another diagonal, another. What do I see? I see a tetrahedron. So that means we have here a tetrahedron that is inscribed into the cube. And this tetrahedron, when you permute the tetrahedron, you basically commute nothing else than the edges of this tetrahedron. Here, of course, you can see that this particular vertex of the tetrahedron corresponds to the diagonal one. Diagonal one is coming out from this vertex. Here, this coming 4. Here it is 3, and this one is equal to 2. So you see the permutations of these vertices. Actually, it is as a part of the cube. It will be also permutation of the diagonal. So you may say, okay, those permutations are even permutations. So this is called the A4. So A4 as the subgroup composed of even permutations of 4 elements. Those are corresponding to the symmetries of the tetrahedron. So to be more specific, you can actually list this. You can list this particular D4 as the permutations of this 5 diagonals. So that you will see that you have here the following elements. So that's a trivial permutation. And then this is 1, 3, 2, 4. For example, so that means this will be like a number 1 diagonal coming here. This is 3, 2, 4. So those are the diagonals that you see from the top. They're coming out of these vertices. And then, of course, take this rotation. This is a rotation. Apply it twice. You are getting 1, 2, 3, 4. And then, of course, if you take the third power of the rotation, first rotation, then you will be getting the inverse one. And this will be 1, 4, 2, 3. And those are rotations. So these are the rotations. And then, of course, you have reflections. You have the reflections, and the reflections can be easily figured out. Just simply this reflection is 1, 2, 3, 4, and then we have here, we have also 1, 4, 2, 3, and 1, 3, 2, 4. So those are the those are the rotations. So I can write simply, this is just simply Z4 relation, and hand out one, this one will be Z4, and I can put here kappa. So similarly, I can describe the subgroup D3 inside the S4 using the same ideas, namely D3 is related to this particular picture of the hexagon. So I have here like this 1, 2, 3. Then those are those are the rotations 1, 3, 2, and then we have here 1, 2, 1, 3, and 2, 3, and those are this one is Z. Those are Z3. And these are the reflections, Z3, kappa. And now, of course, there is also A4. You know what is A4. This A4, those are all even permutations. But there is also another. So we have here A4. Those are even permutations. There is also interesting group. This group basically is the same. Is the same as the product of two Z2 groups. But in our case, I just simply list this as a subgroup of the group of permutation. This is the group, they call it Klein's group. It will be kind of appearing in many examples. So this is 3, and this is 2, 4, and that one is 1, 4, 2, 3. And those are the permutations which are either, this is like you see, two cycles, two disjoint cycles, two disjoint. So those are even permutations composed of two disjoint cycles. So this is 1, 2, 3 such permutations, and one. So this is called the Klein's group. And then let me make a picture. So of course it is all interesting. So how this lattice looks like, I will point out that of course one of the things that we would like to know, is it possible to use computers to get these lattices to look at the structure of the subgroups? Of course, the answer is yes, but it is still a little more complicated, especially for a person like me, to do it, because it requires some programming that already exists and is available, but these programs have to be installed on your computer to use properly, and for me it is very difficult. So I'm sorry, I'll try to show you how to create these lattices in, let's say, in closed future, and I hope everything will work nicely, so I will be able to illustrate it properly. So those are the subgroups. So where is it? So we have here, that one is here, Z4 is here, D2 is here, and of course we have here Z3 is here, and this is D3, and then we have here Z2 standing here. So it goes like this, like this, like this. And then we have here D1, the same level, because this is two elements. And then we have here Z1 here, D1 and Z1. This is D1, D1. And then this is going here, going here. And did I forget anything? Z3 is also here. Yeah. And yeah, I think it's okay. So that's how it looks like, lattice of the sub. So in our case, just recall it, this is basically the set of all conjugacy classes of subgroups in S4. Okay, so now of course, once you have conjugacy classes of subgroups, we would like to consider the group G, which is equal S4 times Z2, and we would like to apply the notation. We would like to apply the notation to this particular conjugacy classes of this group. So we would like to classify the conjugacy classes of subgroup in G. We notice that we have either product groups, so let me just simply list them. So we'll write it down. That means G itself is S4P, product with Z2. So of course then you have here A4P, those are just representatives, D4P, then you have here D3P, then you have here D2P, and then we have here Z4P, and then we have here V4P, and then we have here Z3P, then you have here D1P, and then you have here Z2P, and then Z1P. Good, so we have all this products. So the second one, so this is my A. What about the twisted? So twisted means, of course, you just list S4, A4, D4, D3, then you have here D2, then we have here Z4, V4, Z3, D1, Z2, and Z1. And now we are coming to this, and we have to describe the other twisted. So the other corresponding to the epimorphism. So you have to have an epimorphism from H subgroup of S4 to Z. So this is epi. So we start with the first epimorph. I just call it minus. So it goes from S4 to Z2. So if I call this minus, so this kernel of this minus, guess what it is? This is alternating group. That's of order 2. So that's nice. So we call such a subgroup. So you have here S4, and I put here minus, which is corresponding to this particular epimorphism. So of course, similarly, you can do something similar like this: Z4, and I put here D. So here we have here kernel of such homomorphism D just equal to Z2. So yes, that's a good homomorphism. So in such a case, we have also V4 minus, the same as before, and you can see in this case this will be also kernel is also equal to Z2, and then we have here D4D, D4D, then you have also D4D tilde. So what is here? The kernel here is D2, the kernel for the second one is V4, we call it with the tilde, and then we also have D4Z, we have here D2Z, we also have D1Z, we also have Z2 minus, and this is kernel of this minus is just simply equal Z1. Z1. So did I forget anything? Okay, so those are the subgroups. So the other conjugacy subgroups. Let me check if did I forget anything. In any case, if you count it, so let's see how many we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 12. Okay. 1, 2, 3, 4, 5. I'm getting close. 6, 7, 8, 9, 10, 11. 11, and then I have here 11, and 11 is 22. And then additional 22. So what do I get additional? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 additional, so 31. In any case, we just listed using the. So what is the issue here? So of course I said that if you would like to have these names in certain way incorporated into your, let's say, script of your program, that means you would like to do it. I'll show you in a moment how to do it. So you should write something more simple with no subscripts and subscript or superscripts. I will simply write here, just simply, this will be like a Z1P. I will write here Z5, so this is my capital Z5P. So this would stand for that one. This will be D1P, and that one will be D5, 5P. So this will be abbreviations. So this is what I was calling abbreviations. So in our case, the abbreviation of the subgroup will be like that. So similarly here, I will just call that one D5Z, and then you go and you see here, and you can see the other symbols. So what here? Let me just go and show you what does it mean. This one, for example, it will be written Z4P, and you can guess that this one, for example, that one will be D4 tilde D, because there is a little tilde. That means to distinguish these two homomorphisms. So this will be D4TD, and as I put it as for Z, because kind of a no way to write it, minus. No, I don't want to just to use it as an algebraic symbol. So minus, so this would be the same as this Z. I would say that notation could be applied. So, but that's not what is supposed to be. Let's say very rigid. People can just definitely use their own ideas. So let's go further. Let's consider other possibilities how to create your notation in case of the, let's say, more complicated groups. In this case, you would like to have your notation to, in a certain way, incorporate kind of a symmetric properties that you could identify from the notation. So let me call this amalgamated notation. And what is this amalgamated? So first of all, the idea comes from the mathematician whose name is Burnside. You probably know this when you study algebra. You probably learn about this mathematician. So let me explain what it is about. So actually, Burnside proved that any subgroup of a product, maybe put it like this, of subgroup H of a product, and this will be like our group is the product of two groups, G1 times G2, can be represented as and let me write. So this is our subgroup. No, I don't need equals, and then we have here the subsets H, K, and this belongs to H times K. So what is H? H is a subgroup of G1. So K is a subgroup of G2. And then we write it here that phi of H, that's similar like in the twisted notation, except you have here two homomorphisms K. So what is phi? So phi is going from H to certain group L, and this psi goes from K to the same group L, and both are epimorphisms. Those are epimorphisms. So every subgroup can be represented in this way. So, of course, you can see immediately that it is related to these two subgroups, one here, one there. So this is kind of an important. It is also related to this product. So we have introduced this notation, and this notation looks like that. So instead of writing H in this elaborate way, so abbreviation for this H would be simply something that we write like that. So this is one homomorphism, then you put here L in the bottom, and this is another homomorphism. They are both epimorphisms, and put here K. So this is notation. We call this amalgamated notation or amalgamation notation. Amalgamated notation where phi and psi are epimorphisms. But let's say like this. For us, we are interested in conjugacy, in describing conjugacy classes of H. So maybe conjugacy classes, I put it here like this, of H. Conjugacy classes. So we need to indicate what are the homomorphisms, so epimorphisms, morphisms phi and psi, and in such a way that it's not really necessary to indicate exactly what is this epimorphism, but in the case when this description allows or create an epimorphism, and it does not, let's say, the choice of such an epimorphism according to our description is not colliding with the, let's say, does not lead to another conjugacy classes, so we can actually use the certain the characteristics of the phi and psi to do it. For example, so we need to indicate what are the epimorphisms, for example, by showing what are their kernels, well, maybe like this, showing their kernels. So, what does it mean? So, for example, if A is equal kernel of phi, and if B is equal kernel of psi, so of course, let's say if you have a kernel, so there may be many such homomorphisms, but you are not interested in this homomorphism. You're interested in describing in this particular conjugacy classes. So if it happens, in certain good cases it happens, you can indicate by this particular you can indicate this particular group by using the notations like that. So it can be simplified. I just simply write H is equal, and I put here H, and instead of writing phi, I write here A. So this is the kernel. Then I have here L, then I have here B, and this is K. So this would be like this. If this is not possible to do it, so we can always assume that L is described by that one. So this means, for example, L is definitely K divided by B, or A divided by H divided by A. So if it is not possible to have this unique identification, you can add some additional information, put it here, like down. So let me do it again. So that's the notation. So most of the time, since I noticed that L is equal K divided by B, because B is a kernel, so it's a normal group. So there is no really need to write L in the bottom. So the notation becomes now simpler. I just simply write it down B, and I put here K. So in our computer programming, this notation, the computer will return to you the notation. If you have the names for the group G1, you give the names to subgroups. If you take the group G2 and you give the names to the subgroups, then this amalgamated notation will be returned by the program in this particular form. So this will be H, okay, vertical line A, and then you have this sign times, then you have here B, this will be another vertical line K, and it returns this particular notation. So this will be amalgamated notation. Amalgamated notation. I will illustrate it in a moment. I will illustrate in the moment. So let's go and do, let's say, an example. Let's start doing a couple of examples. So we will use the gap program in order to, let's say, I will show you the script. The script will be, let's say, included in the description of today's in today's lesson. So let me do the example, and let's use the gap program in order to generate the Burnside ring and use the notation that we generated by the, let's say, the names and their abbreviations, and we'll try to understand how this notation can be extracted from the let's say from the multiplication tables for the Burnside ring. So just simple examples. So in our case, we take the G, which is equal D5. So this should be written, G is equal D5 times Z2. So what are the names? So in order to do it, of course, we have to generate. So let me go back and let me pull out the program. So this is my program. Look. So here we start, so this is D5 times Z2, so of course that's D5 times, it's X, Z2. So we will start the gap program, we load the package, then we write group 1 is dihedral group. This name, pDihedral, means you want to define the dihedral group as a permutation group, so you put here P before dihedral group. And then group 2 is a symmetric group. Of course, in this case, symmetric group of two elements is Z2. So no problem. That's our Z2. So you create a product of D5 and Z2. So here the first one is called G1. The second one is G2. So it will be just exactly direct product. We are getting it here. And then once you have the group, what are the conjugacy classes of this group? It's here. The CCS is the conjugacy classes. So CCS, all those names that you are giving here, GR1, GR2, G, that's your choice. That's your imagination. You can make it complicated, you can make it simple. For example, here you could, I wrote CCS names, but you could make it just simple, CCSN names. And then so you see here, those are the abbreviations, Z1, Z1P, Z. How do I know what are these abbreviations? Okay, you have to recognize the subgroups. You have to recognize it. So what we do, let's start. So let me copy it, Control C, and let's start the gap program, and let's play a little. So I go to the gap program, and I start gap, and then it's running. So now I need to copy it. So how it goes? It's copied. I copy the script. You see, I copy, load. Okay, you see how pin. That we should always remember who created it. And now you have two groups, CCS. So yeah, we have CCS. So now we give them the names. So let's write it down, CCS. And let's see what is there. So you look at these groups and you see, start. Here. So this one is the first one. This one is trivial. The second one, you look, that's a, what it could be. What it could be, 6 and 7. 6 and 7. So it turns out that this is nothing else than D1. D1. And then you check next one, because how do I know it's D1? No, that's not D1. No, actually this is Z1P. Z1P. This is Z1 times, yes, times Z2. Why? Because you have 1, 2, 3, 4, 5 are used for the D5. 6, 7 is used for the group Z2. So if you have trivial element in that group, then this trivial element belongs to Z1. This is the generator. The 6, 7 is generator of Z2. So we are getting that this is exactly Z1P. Z1P. And similarly, you go to the next one. The next one is clearly, what is the next one? D1. Check it out. This is just simply conjugation. If you make a picture of a pentagon, it shows that this is conjugation. So going through all these symbols, you carefully recognize what are those symmetry groups. So you come to the following list of the names. So you see these are the names of these conjugacy classes. So you see first one is Z1, the second one is Z1P, then you have here D1, then you have here D1Z, etc. So you put these names and then you associate these names with the conjugacy classes. So let me copy it and let me run it. So I go there and let me run it. So I run it and this association is finished. So now that's it. So we want to have what is the Burnside ring. E.g. Good. And then I choose the H, those are the free generators, so this will be basis AG. And now we can play. So those are exactly corresponding. There are 10 conjugacy classes here. There are 10 conjugates. They all correspond, as you said, to the notation that we have. So we know it. So first of all, let's multiply something. Why not? Find out what it is. And so we have 10. So I put it like this. H number. Okay, move it down a little so you can see what's happening. So H. Okay, let's see. 6 times H 8. And that gives you the product in the Burnside ring. 2 times 6. So this is 2 times. Actually, we know what it's supposed to be because this is exactly the case that we covered. So let's see what it is. Okay, so you can just do everything by hand and you can verify this is exactly what it's supposed to be. But what is actually the CCS? Am I right? Is the CCS? And then I want to know what is this 6 group. What is this? Because I forgot it. Oh, I need to Z5. Because you don't want to go and you don't want to look. This is Z5. That one. 1, 2, 3, 4, 5, 6. That one is number 6. But you can just simply call it. The program will be recognizing this notation. The program will be recognizing notation. So there is no need to memorizing or keeping notes, etc. You can just call it in any moment. So very good. So we have it. So we know how to associate the names, etc. So let's quit. And let's do another example. So this time, let me go back to the nodes. So what do I have here? I have another. And now the group is more complicated. Look, this is D5. This is my G1. So here I want to use the Gursa amalgamated notation. So this is D5 times D3 times Z2. So that one, for these subgroups, because this is D3 times Z2, I can use the twisted notation. So I can list them accordingly to how they're supposed to be listed. Notice that the GAP program always, due to the algorithm, always will assign the same list of the subgroups, the same list. This comes from the algorithms that were used. That means if you use it, if you use this group, definitely will get the same list on the another computer. So we were checking it out. Yes. if there is no problem, you can use, you can create this list of the subgroups and use them repeatedly. So this is the list for the D3 times Z, Z2. So this is the list of the names. Then you have the names for that one. So how the names are assigned in this case? So you write here like this, CCS for the first group, then you take the product group with Z2 and assign the names for this particular conjugacy class. After that, you set the abbreviation. So this is how we set the abbreviation in this group. And we are done. We are done. So that means you have the names incorporated. So what's happening? You have the names incorporated. So let me copy the program. This is Z. Okay, good. And let's go to the program and start the gap again for this particular example. And I have it. So now I put the script and I created it. So I have the abbreviations and we are done. So what else I can do it? So let's go and generate the BurnsideRing. So make sure that I'm using here. So I have here BurnsideRing. And let's run it. So we have 69. So look, size of this CC. Let me check. This is CCS, 1S, I believe, right? Yes, 69. So this is the 69th conjugate. But you would like to know what is this conjugacy class? Remember, that case, actually here we are dealing with the finite product of two finite groups. In order to know what are those classes, you just write amalgamated notation, symbol. Amalgamation symbol. And we can check, for example, CCS 68, CCS, and this will be 68, close it and set, and find out what do I get. I'm getting this particular symbol. And what is the meaning here? Where's my pen? Let me write it down. So D3, Z3, D3Z, and this is D3P. So look, let's go and identify it. So what do I get? I'm getting here, this is the case. So let me underline, this is G is equal D5 times D3 times Z2, and we have here two symbols, namely that one. We got this one. So this is D3, and here we got it Z2, it was written like this, D3, then you got Z3, 10 was D3Z, and then you have here D3P. So that's what computer returns, and then the amalgamated notation in this case will be like that. This is D3, Z3 is at the top, then convert that one, this is D3Z, and that one is D3P, and you can see clearly this will be Z2 standing here. So it gives you kind of an idea that this is kind of a, let's say, two symmetries. One on the one space act as a, one group acts as D3Z3, another group, maybe I should use double, because this is side, no, this is Z, and this is subgroup, okay, Z3, and then the other one acts like D3P, means D3 times Z2. Yeah, we got it. So maybe Now you would like to multiply something. Let's multiply something and find out what is this. So we have it. You have the amalgamation symbol here, and okay, let's multiply. So I say h, and here I have here 68. I multiply h 68 times h 53. I don't know even what is 53. Yeah, I got it. 2 times 53. Huh. What is H53? CCS. So amalgamation symbol. And then I have here CCS, and this will be 53. Correct? D3Z3, D3Z, just a product. This is just a product. You see, we got, so we have an idea. We got how to use these things, how to verify the multiplication. Of course, if you would like to have a full multiplication table, yes, you can just simply check all this multiplication, fill it. This is a big table. We understand that eventually, from the practical point of view, once you start dealing with the group, which are kind of elaborated, kind of large, there will be no way, in the physical sense, create multiplication tables for any kind of the, let's say, visualization. This would be impossible. This will be impossible. So basically, that's how it looks like. So let's go back to the notes, and I will continue description. So let me go down and let me point out another thing. So let's go now to the infinite group. So our example of an infinite compact Lie group will be the elementary, the simplest, non-trivial, non-abelian group, which will be, in this case, I'll put it like the example, Lie group compact, let's say non-abelian Lie group, in this case, is the orthogonal group O2. So this is orthogonal group O2. So this is our group O2. So let's do it. G is equal O2. And phi of G, so what is the phi? So those are the conjugacy classes of subgroups with the Weil group being finite. So means of dimension 0 as a manifold. So what are those classes? So of course O2 itself, Weil group trivial. Then SO2 you can compute easily that this is a normal subgroup, Weil group is Z2. And then you have here Dn, and here n is equal 1, 2, etc. And normalizer of Dn always in O2 is D2n, very easy to verify. So you are getting here, those are the all conjugacy classes of subgroups with a finite Weil group. So there are no others. So there is another one, this phi 1, which we do not consider. In this case, this is just simply Zn. So n is equal to 1, 2, etc. And notice that Zn is normal. Zn is normal in O2, and O2 divided by Zn is again O2, isomorphic. So the dimension of this Weil group, dimension of the Weil group of Zn, which is equal, is 1. So it is not in this one. So this definitely does not belong here. So we do not really need that one. Because the Burnside ring, AG, is exactly generated by the conjugacy classes of those with the 0-dimensional Weil group. So We got it. So let's see. I have this one. Let's find the multiplication table. Let's find the multiplication table. So here, turns out that we can do it with no problem using just computations by hand. So here we have O2. Remember, O2 is the full group, so G is equal O2. So that conjugacy class acts as identity. So this means that we don't need to compute anything. We just notice it in the construction. And then you have here also dk and k, and then you have here O2 standing here. And then you have here SO2. And finally we have here dn. So easily, that's identity, so you just copy it. So there is nothing to do. That means also here SO2, and then you have here dn. And then easy to notice is also that SO2 times dk is 0, because you can immediately notice, what you're noticing, that orbit type, because if you take O2 divided by SO2, and then you take it intersection, and this will be like, and then take it with intersection O2 divided by dk, or dn. So what do I getting? So the isotropy subgroups will be O2, intersection, and then you have G, dn, G minus 1 is always equal to Zn, and Zn, as you notice, does not belong to phi 0, it belongs to that one, so it's not there. If it's not there, it's 0. So okay, I'm getting here dn 0, this is 0. So now let's compute the product of dn times, so dn intersection G dk G minus 1, you will find out that that one has two values. This will be dl or zl depending on G, and in our case L will be equal greatest common divisor n and k. Since that one is not in the phi 0 but in the phi 1, so only dl. So we can write it down that the product dn times dk will be equal x some integers, and then this will be dl. And now we can compute this x. This x actually using the formula is easy to compute. We have this recurrence formula, so it will be n and will be dl. This will be dn, and this is Weil group of dn, and this is n, and this is dl, and this is dk, and this is Weil group of dk divided by Weil group of dl. And now we already mentioned all the Weil groups have two elements, so this will be two elements, Z2, and that one is 1, this one is 1, this one is 1, so we get the value is equal, sorry, not 1, 2, sorry, this one is 2, so cancel, we are getting 2, so let me put it back to the, I'm getting here 2 dl, and not to spend too much time, just simply write SO2 also 2 by the same reason, because if you look at the formula, you can replace you replace the let's say SO2 by all these values by SO2, you'll be getting the same values. So Weil group is again 2, and SO2 in SO2 has the NLH number 1, 1, 1, so this will be the same. So basically we did it, we're done. So how to generate O2, group O2 in the gap? So let me go and let me discuss the program. So let's go to next example. And in next example, we have the group O2 times D6 times Z2. Yes, I changed the computer. The Windows crashed, and that's supposed to be not unusual. So I had to move this presentation to another computer. So we will try to finish it using my Mac, and that's why the outlook is a little different. So let me continue. We have the one more example. So put it like this: example. And in this example, we consider the group G, which is the case of the compactly group. So we will look at this as the product of O2, and this will be times the group gamma. So this is D6 times Z2. So we know already how to generate so we'll look at this one. Let's select this. So this will be our group G1, this is O2, and the group G2 is the group D6 times Z2. So we know how to generate the conjugacy classes of subgroups. So we will actually consider that one, G2. G2 in our program seems like a little different, so this will be small g1, and we will be generating the conjugacy classes of this group G1, and we will also generate conjugacy classes G1 names. So we will basically do the following. We will look at the conjugacy classes, its generators, and we will recognize using the twisted notation, what such a subgroup represents. So we will give this name. So actually, let me show you right now how it's going to work. So I'm going to bring the gap program in front. So let me start the gap. Gap is here, so this is gap, and we're running the gap, and now I'm bringing the package. First I take the package, and then I will generate the groups that I need to work with. So I'm coming here and I start it. So as you see, we have here the following. So first of all, I started the package, and now O2, little small O2, this will be orthogonal group over real. Very good. And then we have here, this is of course the compact group, so this is the conjugacy classes of subgroups. Infinite set, you don't expect that computer will hold them all. So what do we do next? We generate the group D6, it's a little small D6, so this is P as a permutation group, dihedral group of 6 elements. And then we have also Z2, you could write it down that this is a cyclic group, P as a permutation, or you could just simply write this is symmetric group 2. And then you have the product, so G1 is the direct product of D6 and Z2. Once we have this product, we can do the following. So first we go and find the conjugacy classes. So let me do the following. I will just simply write it down. So you see the conjugacy classes, as I indicated, of the subgroups of G1. So let's do it, and we have it. So after that, we have a very careful look what they are. So of course we have here like this the D6 is permits 6 elements, so 7 and 8 in this operation. It means simply it comes from the generator of Z2. So in this case, if you write all the subgroups, you will look at the generators, and then you will be able to recognize what those subgroups are. So let me, for example, give you this is CCS G1, and then let's say like this number 1. And you go, oh, that's a trivial group. And similarly, you go to all the number 2, and you find what it is, and you recognize what it could be. So you can see this is definitely tilde D1. Yeah, that's how it works. You can have a hexagon, and you see that this is a hexagon. That's a symmetry, that's a reflection of hexagon, which is not the reflection that corresponds to the usual conjugation of complex numbers. So, and so on, you can go further. So after doing this, you have the list of all the names of these conjugacy classes. So let me just simply put these names into the program. So I got it. So I just record these names. Sorry, something happened. I have to do it more carefully. One more time. Where is my, okay. So let me do it again. Those are the names, as you see. Did I, no, I didn't, still I didn't do it correctly. I did not copy it correctly. And then, okay, so let me remove these things. Delete everything. Oh, maybe I have to do it again. So do it again and enter. Now I have the names. Those are the names. And after you have these names, you associate the names to the corresponding conjugacy classes. So you put it here. This is your V, and that means abbreviation, means set abbreviation or set the names, and we got these names. Now there is a time to generate the group. They generate the group O2 times D6 times Z2. So let's see how it goes. So let me do it here. Again, let's have to close that one, otherwise it's coming. Okay, V. So you see this is the group O2 D6. So this is O2 is already generated. G1 is D6 times Z2. Do it. And the group is generated. The group is generated. So now I am going to create the, let's say, make the conjugacy classes of this group. And of course we cannot display, there are infinitely many of them. So those are the conjugacy classes. And it takes a little time, so let's wait and let's see what happens with these conjugacy classes. So this conjugacy classes, actually, when I was using the Windows computer, crashed the Windows. So, so let's see if actually that one works. Still working, as you see, still working. Being patient. So that means it is actually taking time. So I cannot kick, let's say, I cannot accelerate just simply by giving the orders. So we have to patiently wait for for the program to conclude and see what happens later. Yeah, still working. So in meantime, maybe I will prepare my next step, and basically I will. Oh, it generated. So we got the. So let's see what it does. So as you notice here, we will have two. You see, this is conjugacy classes. Maybe I write it down. CCSS, and this will be G, and it is generating this conjugacy classes, but it is using two indices. So the first one, 2, is related, we call it, to the Fourier mode. So that means it is related to the group O2. And as you understand, we believe, let's say, in this case, the subgroups of O2 are clearly given by the decay. Those who are that are in the Burnside, this is decay. K in such a case will be denoting the Fourier mode. So this will be like a K is related to the group decay. So if this is D, if this is D2, so this will be 2. So let's see what do I get. And fortunately for us, this conjugacy class comes in the form of a, let's say, of a symbol that can be that is actually amalgamated symbol. So we are getting amalgamated symbol immediately, and of course in such a case we can easily, let's say, translate it into the notation, amalgamated notation. So let me write it down. What is the amalgamated? So this is D4. As I said, this was D2. So the D4 is standing here. So let me see. Let me do it like that. Where is this amalgam? Oh, here. So this will be D4 Z2, and then I forgot. Yes, D1 D2P. So this is D1 D2P. So let me write it. So this is D1 and this is D1P. Remember, D1P is just simply D1 times Z2. D1 times Z2. So that part is corresponding to the D6 times Z2. This one is in O2. So you see this is D4 and this is divided by Z2. Okay, so that's the group. In this case, I think 2144. Okay, so we understand that this notation can be retrieved. And now let me generate the Burnside ring for this group. So what I'm doing here, I'm just generating the Burnside ring, and H will be the free basis. I have it, and why not? We can just simply multiply something. We can multiply something. What about if I multiply these two elements? The one that we looked at and another one. Okay. So the multiplication is again slow. I don't know, I didn't produce. Oh, actually it was quite fast. So we got that this product of these two generators is actually the sum. 1, 2, 3, 4. 4 elements. So what do I get here? I'm getting here, this is CCSG, and this will be CCSG, it must be in the subscript G, that's how we did it. And then we have here, first element is 211. So what is this element? Maybe I copied something? Let me see. Oh, of course, I forgot S. So this is one more S. Oh yeah, I got a I got an amalgamated symbol for this group. I can easily recognize what kind of symmetry it is. What about the 214? Okay, let's check it. 214. If I check it, 214. So what do I get? I'm getting is another amalgamated symbol. Another amalgamated symbol. So what it is? What is the next one? 2, and this will be 28. Go, check it. 28. And as you see, in such a case, I can definitely recognize all this group, let's say subgroups, and I can give them the amalgamated notation. That means it will allow me to easily represent them as a permutation groups and let's say subgroups, permutation subgroups, as you see it, and related to the group O2. What about the last one? This is 73. So this is 73. 73. Yeah, so you got all of them. So now we can just simply copy and write the product of this multiplication. Very good. So we will be using this particular options, these functions of the EquiDeg package later when we will be computing the equivariant degree, and we will be using this equivariant degree to detect and classify the solution sets of the certain symmetric equations, and that is enough for today. So let me finish this lecture, and we will see soon. In the lecture 13, I will start introducing the notion of the equivariant degree as an element of the Burnside ring. So thank you for now.